I would like to thank the IEEE Cloud Summit organizers for inviting me back for a second keynote. This is a super honor, and it adds pressure for showing you some worthwhile new findings. The talk will be self-contained, making it more accessible to those who have not heard of Millibottlenecks. For my fans who have returned to see this sequel, I am happy to report that in the brief span of 1 year, the Millibottleneck story has become much more interesting. And before I start, I need to recognize the support from and collaboration with many PhD, MS, and undergrad students, as well as the industry and academic partners listed here. From the beginning of millennium, e-commerce and web-facing applications have been running in the cloud. The successful applications quickly converged to N-tier architectures that provided much-needed performance scalability. However, their success also imposed higher expectations on their performance, particularly the user-perceived latency. The Elba WISE project started around 2004 to study the well-known but little understood phenomenon called latency long tail in the web-facing application. So, over the last 20 years or 15 years, web-facing applications have evolved, and the requests that they have usually have a relatively short duration, typically in milliseconds today. But they have light resource requirements, usually fetching or updating a small amount of data in memory or in databases. However, they have demanding quality of service requirements, for example, consistent and very fast response time on the order of milliseconds. In the WISE project, as enterprise applications evolved over the last 20 years, we have added more benchmarks to our experiments, and our findings have been confirmed in 3 representative benchmarks: RUBBOS benchmark for N-tier architectures, BuzzBlog benchmarks for microservices, and Dracaena benchmark for data streaming. Our results are consistent and reproducible across all these 3 benchmarks, although we often use RUBBOS as the easiest to explain illustrative example. So before we start on the technical side, we should mention an Amazon study showing the loss of 1% of sales for every 100 millisecond delay in user response time. Since latency long tail translates directly into lost customers and revenues, every company cares about that. This serious concern for latency is one of the reasons cloud service providers must guarantee quality service as an integral part of their service level agreement, usually abbreviated as SLA, and SLAs contain concrete specifications of service level objectives, or SLOs, for example, 1 second user level response time at 95 percentile. Many years ago, that was the case, and as we succeeded in providing better and better performance, the SLO got pushed to 99 percentile, usually abbreviated as P99, and at the same time, as NTIA evolved into microservices, the SLL response time became sub-second. There are several ways to represent and show the latency long tail problem. So in the right graph, percentiles, in this case P99 for example, are cutoff thresholds for subset averaging. In the graph, each subset is divided into two classes, normal, which is blue, and long tail, which is red. And the two classes are shown with their respective average response time, and we can see that the low percentiles near the origin of the graph only have low average. The latency long tail problem becomes significant and visible at 99 and 99.9 percentiles, when their average becomes visibly longer. And the red bars also show the amount of long tail messages. In the left graph, we show the x-axis indicating response time in milliseconds, and y-axis showing a log-scale bar graph of the number of requests measured within each 50 millisecond window of response time, which is shown on the x-axis. In contrast to the two-class bar graph of percentile-based subsetting, in the right side, the all-inclusive left graph shows a global view of all requests, corresponding to a detailed breakdown, typically at 50 millisecond intervals, which is 100% percentile. We will use the left graph for most of the cases to illustrate the fine points of this talk. To summarize, the latency long tail consists of a small number of requests that take a long time, several to many times the average response time, to return. Our research on long response time requests, abbreviated as LRT, and very long response time, abbreviated as VLRT, which is a subcase of LRT, show that LRT requests can be divided into two types. So type 1 requests actually consume a lot of resources, relatively speaking. For example, a web search with many returning matches, which would require database read a lot, and a database grouped write operation with a large amount of data being pushed out to disk. And another example that we'll show is garbage collection. So type 2 LRT requests, in contrast, only take milliseconds when executed by themselves. In other words, they are intrinsically fast. But some other factors delayed their response. As we found out, type 2 LRT requests are caused by transient queuing, which arise during transient resource contention called Millibottlenecks. I will briefly explain type 1 LRT requests, which are similar to traditional performance bugs. After type 2, we will focus on after type 1, we will focus on type 2 LRT, which are more challenging and interesting. In the context of web-facing applications, type 1 LRT requests are associated with persistent resource bottlenecks on the order of minutes, which are detectable using normal monitoring at sampling periods of minutes. The 99 percentile graph shows a few problems with 1 day with sampling period of minutes. The same period looks quite different, however, with 99.9 percentile. So, at a normal coarse granularity monitoring, it is challenging to pinpoint concrete root cause of problems. In this case, a graph of 99.9 percentile showed many more low latency problems due to the inclusion of the LRT range from 99% to 99.9 percentile. This particular problem was eventually guessed and eliminated by copy avoidance, which reduced a critical memory bottleneck that remained invisible at their coarse grain monitoring. We note that type 1 operations may not themselves be web-facing requests, but batch system internal operations. Examples of approaches to address type 1 problems include 1. Additional hardware resources and/or replicated or redundant executions of the same request, hoping that some of them will return fast. Second, critical path software debugging to reduce resource consumption, which is what happened in this particular illustrative case. Or 3, rescheduling of resource-intensive system operations in order to avoid the persistent resource contention. This example illustrates the main difference between Type 1 and Type 2 LRT requests. Type 1 often have an identifiable resource hog that can be found and fixed, but Type 2 that is purely due to queuing would prove to be much more elusive and interesting. So, Type 2 requests come from web-facing applications. They are short, lasting a few milliseconds. They come in fast, thousands and tens of thousands concurrent users in the workload generator, and they have bursts that can be dozens to even hundreds of times that of sustained load. The bursty workload is one of the unique features of web-facing applications. When something interesting happens, users all start using the app, causing sudden spikes in workload. These inevitable bursts cause Type 2 LRT requests, which are reliably reproducible from the workload bursts and actually other causes. In our benchmarks, all requests consume a small amount of resources, so by the construction they cannot be Type 1. We confirm this by adding unique identifiers to all requests and capturing all the LRT requests through fine-grained event monitoring. Then we run these individually identified LRT requests by themselves. Invariably, they take only milliseconds, as Type 2 should. So the first hypothesis of this talk is that Type 2 LRT/VLRT requests are caused by transient queuing during the bursts. In turn, the queues are caused by transient resource contention periods called Millibottlenecks. As an aside, Type 2 LRT requests are interesting examples of reproducible Heisenbergs. Jim Gray coined the term Heisenbugs. Jim Gray coined the term Heisenbugs to refer to bugs that disappear when you try to reproduce them. Type 2 LRT requests are transient queuing effects that appear and disappear, which may not fit the traditional definition of bug, since they are not errors in the system that can be fixed. From type 1 point of view, a natural question is why bother with random and transient queuing, since they'll go away by themselves after a little while. Type 2 might appear to be negligible mosquito bites that don't hurt the system in a big way, at least not as bad as type 1 LRT bugs. The problem is that during the last 20 years, N-tier architectures gradually evolved towards microservice-based architectures for many good reasons, including latency guarantees. What used to appear to be an elusive mosquito bite in N-tier applications, which will be millisecond delay in one server, has become a much more complicated situation in increasingly complex microservice-based systems with many dependencies. This is illustrated by the evolutionary sequence of system components from upper left, which is N-tier, to lower right, which illustrates microservices. So, let us consider a concrete scenario to illustrate the latency long tail problem in the context of microservices. First, the 99 percentile means 1 out of 100 requests will take longer than 99% of requests executed. Second, let us consider user-level services composed of microservices with a sequential invocation train of length 10, which is a common situation today. Actually, the chain grows longer every year. Third, a customer makes multiple service requests per visit, which is also a typical scenario with web-facing applications. As illustration, let us consider the case of 10 requests per visit. The probability of delay for each service is 10 times the fast service time, which is 10 successful executions at 99%, which would result in 0.0956, which is 9.56%. If a customer makes 10 service requests, the probability of the customer being affected by a delay would grow to 95.6%. This means that almost every visit will suffer a QoS failure at P99. This is a big problem, not to be easily dismissed as mosquito bites. So this is the first application of the Millibottleneck theory, and restating the first hypothesis, Millibottlenecks, defined as transient resource contentions, last long enough, for example, hundreds of milliseconds, will create transient queues. In turn, some of these transient queues are long enough to create type 2 LRT requests. Just as an aside, we are avoiding the word bottleneck because traditionally it has been used to describe persistent or permanent bottlenecks. To avoid that connotation for millibottleneck, we use a neutral term for resource contention. Now, we switch to the second application of millibottleneck theory in a quite different area, which was not originally directly related to to workload bursts. Quite a few of us have been affected by a recent wave of ransomware attacks that resulted in huge ransoms, including Colonial at 4.4 million and JBS at 11 million. This is contrast to some of previous attacks that did not get paid. For example, Atlanta city government chose to refuse paying the ransom and instead spend money fixing their IT system. In recent attacks, the attackers got the victim to pay huge ransoms not because the bits they encrypted. The attackers created immediate and rapidly accumulating revenue losses by shutting down entire businesses. Attackers used a strategy that we call pseudo-owner exploit, since they gained full control over the entire victim system. Companies in transportation, the case of Colonial, and perishable groceries, the case of JBS, are examples of businesses with thin profit margins but large daily expenses, making complete shutdowns very costly. Of course, the attackers knew this and chose them as the most vulnerable targets. From a technical perspective, the important observation is that a complete shutdown required full control over the target system, which enabled the deletion of all backups. The pseudo-owner exploitation is quantitatively and qualitatively different from historical ransomware attacks when they only hijacked bits. So, you might have wondered, how do attackers gain full control of the target system to exercise pseudo-owner exploit? We outline the pseudo-owner exploit in 3 functional stages. In stage 1, attackers use penetration methods such as phishing to gain a foothold within security perimeter. In stage 2, from the foothold, they run lateral movement jobs to expand and propagate attack control over the admin nodes of the target system. In stage 3, after gaining full control, the attackers run pseudo-owner exploit, which includes shutting down entire businesses. To gain full control successfully over the entire target system in stage 2, the propagation by lateral movement has to be sufficiently fast and stealthy. Otherwise, the propagation attacks could be discovered and disrupted before reaching the pseudo-owner state. Security companies have reported such discoveries in the past, which actually disrupted the attempts to reach pseudo-owner. The attackers were either too slow or not stealthy enough, or both. So how did the recent attacks such as Colonial and JBS succeed in getting full control without being detected and stopped? They couldn't do it the normal way without detection. It is actually not trivial or easy to propagate attacker control from the initial foothold to the entire target system. Although techniques and tools for privilege elevation and credential dumping have existed for some time, they consume significant resources. For example, scanning entire memory, periodically searching for admin credentials can consume significant CPU and memory bandwidth. Similarly, constant monitoring network traffic to find admin password can consume significant resources as well. These propagation tasks, called lateral movement, can be discovered because of their resource consumption. Our second hypothesis is that the attackers may create transient resource contentions, also known as Millibottlenecks, to obfuscate their lateral movement activities. For example, if the attackers make copies of legitimate application requests and run them in bursts at the same time as the lateral movement jobs, it will be challenging for the normal system monitoring tools to distinguish the obfuscation jobs, which are copies of legitimate jobs, from the lateral movement jobs. So, restating hypothesis 2, successful obfuscation by Millibottlenecks may facilitate attackers gaining full control with reduced probability for detection. A quick summary of the two hypotheses is that transient resource contention, also known as Millibottlenecks, can explain two very different kinds of problems. First, the latency long tail, and second, the new malware attacks that gain control over the entire target system. So now in the second part of the talk, I'll provide supporting evidence for hypothesis 1 and 2. And first, we're going to discuss the latency long tail by type 2 LRTs. And this is done primarily using RUBBOS benchmark. And the same results have been confirmed with microservice benchmark and data streaming benchmark. But because of time constraints, we are not going to discuss them. So first, from the normal benchmarking point of view, we have response time throughput of a RUBBOS, in this case a typical 3-minute benchmark run. And if you average the response time and throughput over the entire 3 minutes, then you'll find a pretty normal looking response time, 80 milliseconds, and throughput in this case will be around 1300 requests per second, and is way before the knee that would prevent, would cause the bottlenecks there. And so what happens is it looks very normal, but when we look at instantaneous response time, then we discover the very long response time requests. So what happens in this case is that instantaneous response time is calculated as not average of over 3 minutes, but rather the average of response time of requests that started for each window of 50 milliseconds. So by calculating the instantaneous response time of a request, we can see the very long response time requests, and they add up to about 2% of a request in this particular experiment. So the latency long tail, in this case, the very long response time requests at 3 seconds or longer appear, and then we can show that they are caused by Apache queue overflow. So the VLRT episodes in this case coincide with Apache queues, in this case a combination of TCP buffer, which is by default 128, plus the thread pool, which is 150. They become full and then cause the very long response time request. So this is a mystery because Apache doesn't have bottleneck of any kind. All the resources are have very low utilization. So eventually we searched through the entire system and found that Tomcat actually exhibits the queuing at the same time as Apache, and Tomcat has associated CPU Millibottleneck and at exactly the same time. And turns out that Tomcat's CPU Millibottlenecks are coinciding with Java Virtual Machine garbage collector. So now we know that the garbage collector, which happens at exact times, cause the CPU Millibottlenecks, and the CPU Millibottlenecks in this case will cause the queuing. and then very long response time by request. So the sequence happens on Tomcat first. So first, JVM garbage collection causes CPU millibottlenecks, and then the second step is that Tomcat millibottlenecks causes inbound queue to be full on Tomcat, and that is 50 thread pool full, and that causes a phenomenon that we call the cross-tier queue overflow to Apache. And in Apache at first, all the outbound the thread pool, 150 thread pool gets full, and then the TCP buffer, the inbound buffers get full, 128, and then start to drop packets. The packets that get dropped get retransmitted after 3 seconds, and they become the very long response time request, and that causes the latency long tail type 2. So to prove this was the case, we removed Java garbage collector millibottleneck. We were lucky that we got JDK 1.6, which had a new garbage collector, and the problem just disappears. So just by simply installing the new JDK, the millibottlenecks and the latency long tail disappeared for this particular experiment. So we were able to reproduce the problem for a variety of situations, and 2 of them that we spent time to produce the data were DDFS, anti-synchrony. So in this case, on MySQL, we have millibottleneck because MySQL uses more CPU, and when MySQL has low utilization, the DDFS would slow down the clock, and that causes CPU millibottlenecks the next time when a burst of queries come in. And MySQL in this case fills up the inbound queue, and then that propagates the cross-tier queue overflow propagates to Tomcat, and then when Tomcat's queue becomes full, propagates to Apache, and Apache starts to drop packets after the Apache queue overflow. So this is a similar sequence of events caused by a very different mechanism. And third one is a little bit more interesting. So noisy neighbors in consolidated virtual machines, and this is part of any cloud. Of course, our hope to increase cloud utilization. So in this case, on Tomcat, we don't need to go. I mean, we could actually build this experiment on many different combinations, but the simplest one is just simply on Tomcat. We have bursty neighbor that generates CPU millibottleneck, and that causes a problem with inbound queues, and then cross-tier queue overflow to Apache, and so the same things happen there. So instead of garbage collector, we have the noisy neighbor injection, and that causes the different shapes of queues, but the results will be the same. So we have found many kinds of millibottlenecks, CPU millibottlenecks. In this case, 3 examples: system software, which is Java Virtual Machine Garbage Collector, DVFS anti-synchrony, and virtual machine consolidation with a bursty workload. We also found memory and disk millibottlenecks, in this case thrashing, that happened, and also other millibottlenecks like the lock contention. And the millibottlenecks in this case required instrumentation, fine-grained instrumentation to find them. So 5 stages, and due to time constraints, I will not be able to go into a lot of detail to describe it. I will just mention briefly and you can find more details from our website and papers that described quite a few of those components. So the first part is benchmark experiment generator. So Webflow workflow specification tools that allowed us to parameterize for many NSF cloud software hardware configurations and benchmark configurations. So now we have three benchmarks: the RUBBOS N-tier, the BuzzBlock microservices, and Dracaena data streaming. So one thing to point out, in this case, not just us, but other people also, is that we need to have very fine granularity in time sampling, so we can get a better picture of what's going on there. So on the left, sampling at 1 second, you don't see much, and on the right, sampling at 1 millisecond, so you can see the rise and waning of interesting Millibottlenecks in this case. So the second part is event and resource monitors. So we need to have fine-grained resource monitors of CPU, I/O, and memory and disk, for example. And we use collect-L SAR, and we also use IOStat at 15 millisecond sampling rates, and lockstat to find lock contention. So we use specialized snippet of code to record the departure arrival of messages at every server, and this is done using specialized code generated using eBPF. And last year we also developed container level monitoring, which also provides a very fine-grained data collection. So this is a lot of data. We generate gigabytes of data every experiment, and they have a variety of configurations and data logging data output formats as well as content. So we have a tool called PerfDB that ingests this data and cleans it up and loads it into data warehouse. So the data flow in this case consists of primarily two sets of monitors, the collect-L and the SAR resource monitors, and then specialized event monitors as well. They generate pretty much CSV files that are going to be interpreted and imported into the data warehouse. So the data analytics in this case goes through a pipeline. So PerfDB starts with pipeline, and then we detect the Millibottlenecks as well as finding the causal events to correlate the data that we have with the theory. And in this case, we have a profile, and we have 99% percentile response time, which is 20 milliseconds. And then we have very long response time requests on the right side, and the long response time requests, LRTs, in the middle. So these data is now fed into an automated analysis teamed ensemble classifier, and called PerfML. And we are able now to analyze a lot more data than before. So our past papers on Millibottlenecks were on a part, say 20 seconds segment of an experiment to demonstrate the relationship between the data we have and the VLRT requests. So with PerfML, now we are able to collect and aggregate data from many different experiments. So this is a class from spring 2020, and about 500 RUBBOS experiments. So we can find, for example, CPU Millibottlenecks in all the 4 servers, Apache, Tomcat, CJDBC, and MySQL. And number 2 is disk, so that's for 3 out of 4. So these kind of population studies will show us where the likely bottlenecks are for this particular benchmark. And in this case, long response time diagnosis is correlating the different components of the data sets with the transient queuing, which is the Millibottleneck hypothesis. So generally speaking, in practice, the cloud service providers keep the cloud utilization at very low levels. So for many years, we have less than 20% average utilization. And the advantage is that they can focus on type 1 known bugs. And disadvantage is that they don't actually know too much about Millibottlenecks or type 2. And what happens is when we have a big crash, and we have had quite a few of those recently with all the major service providers. So Microsoft, Google, and Amazon all had significant crashes or unavailabilities. So we will be continuing our studies and looking for the match between the bottleneck hypothesis and real-world phenomena. So I wanted to mention that last year's talk, I had this slide, and I talked about latency long tail, I talked about the low utilization, and I actually mentioned that Millibottlenecks not exploited in systematic attacks. And one question, which I conceded to be reasonable, is why study a virus if no pandemic? And that changed this year with the Colonial and JBS attacks. Huge ransoms paid this year due to attackers gaining full control and using pseudo-owner exploits. The main difference between the new generation of those malware attacks and the previous generation ransomware is the full control and pseudo-owner exploit. So it's important in this case for us to figure out how they are able to do this. So hypothesis 2 says that the Millibottlenecks, when generated for this purpose, can make it more difficult to detect the resource consumption used by lateral movement jobs. So we're going to briefly discuss how this could be done. So first, we want to make clear that the main reason they are able to get huge ransoms is because they have the pseudo-owner exploit, and the pseudo-owner is achieved by lateral movement jobs that succeed in gaining full control over the entire target system. And this is done through toolkits like privilege elevation and credential dumping. And in this case, these operations are very resource intensive, so they will need to obfuscate lateral movement to increase efficiency and stealth to minimize the probability of being detected. And these are what we call the speedy, stealthy propagation jobs, SSP jobs. So they consume more resources, but they're not being detected. So obfuscation of SSP jobs in this case is accomplished through a tool called Denial of Quality of Service, DQoS, and it is a controlled injection of copies of legitimate requests and shape combined attack workload. So the combined attack workload in this case by construction is the SSP plus the obfuscation, which would look like a legitimate workload, and because they look like their sum, the total load would look like legitimate workload. So that would make it difficult for pattern-based detectors. So the idea in this case is that we will generate the load as on the left side, and then the right side shows that the generated obfuscated SSP jobs, the orange line, will look like the legitimate, which is the blue line, dark blue. And then when added together, they will look like the total load, in this case the gray line, will look like the legitimate as well. So the construction of obfuscated SSP jobs is that we need to calculate what is the time-varying legitimate load. And legitimate load in this case can be done by subtracting the attack load from the total. And in this case, then once we have the legitimate load at a time window, we can use that to estimate the next time window, and then we use that estimate to calculate the amount of DQoS obfuscation that will be needed, and then the WISE toolkit will generate the right amount of DQoS. So we mentioned that the obfuscated SSP jobs will be difficult for pattern-based detectors to find because they look like the legitimate workload. So our hope is that we are able to generate profiles on Millibottlenecks and the resource consumption as well as the response time. So what we're hoping for is that the WISE monitors will gather enough data so we can distinguish, as suggested by the left side, the normal workload from the heavy the heavy-tailed workload which would be expected from resource-intensive SSP jobs. So this is something that only we can do with the kind of fine-grained monitoring, data collection, and data analytics that we have been developing in the WISE project. So Millibottleneck theory is maturing, and in this case, from hypothesis 1, Millibottlenecks will become more prominent in microservice-based applications. And they're growing fast in scale and complexity every day. And hypothesis 2 says that Millibottlenecks may become an important ingredient in getting full control of target system to achieve pseudo-owner exploitation. This is quite scary, but we also have ways of still detecting the camouflaged, obfuscated the jobs, attack propagation jobs. So as long as we stay ahead of attackers, we have a chance of countering the different ways of, for example, push for full control of target system. So generally in science, theories mature by providing explanations for more interesting phenomena. And even though in computer science we don't do this a lot, this is happening with Millibottleneck theory, and it's really exciting for me. So another discovery this month is that there is a new virtual conference called P99 conference, and they do talk about latency long tail there. So the community is growing up, and we are seeing more attention being paid to this problem. So to summarize, Millibottleneck theory explains two classes of phenomena. One is latency long tail of anti-tier and microservice-based systems, and two, obfuscated lateral movement to achieve pseudo-owner exploit is a very important problem, and we need to find different ways of detecting lateral movement even when they are being obfuscated. So the WISE toolkit, in this case, carry out Millibottleneck monitoring and analytics, and it's been very useful, and we share it. It's available to partners as well as general public. So the impact of understanding Millibottlenecks, we believe, first could help service providers and application designers to achieve higher cloud utilization while avoiding the latency long tail. And a second part is that the detection of malware propagation before they reach full control is very important, because the pseudo-owner exploitation is much more expensive, more difficult to handle than being able to decline their invasion in the first place. All right. Questions?